In today's video, we'll learn how gravity affects freely falling objects. When do we consider an object freely falling? An object is considered to be freely falling when it's moving freely under the influence of gravity alone. The magnitude of free fall acceleration is symbolized by lowercase g. On Earth, the value of g is approximately 9.8 meters per second squared. The motion of a freely falling object is the same as the motion in one dimension under constant acceleration. The upward direction is usually defined as the positive y direction. So in the case of a freely falling object, the acceleration is equal to negative g, or negative 9.8 meters per second squared. We can see the effects of a freely falling object in our problem below. Our problem says if a stone is thrown from the top of a building with an initial velocity of 20 meters per second straight upward at an initial height of 50 meters above the ground, the stone then falls and hits the ground at the base of the building. Determine the time needed for the stone to reach its maximum height. So to start, let's list the information that is given to us. So we know our initial velocity is 20 meters per second, and the height of the building is 50 meters. And we're asked to find the maximum height when the stone is thrown upwards. So we're trying to solve for time. So if we use our equation where we have final velocity is equal to our initial velocity plus acceleration times time, we can solve for t, considering we know acceleration, which is our gravity on Earth, our initial velocity, which is given to us, and then at the top of our throw, before the stone starts to fall back to Earth, we'll have a final velocity of 0. So we can rearrange this equation to solve for t. And if we do so, t will equal our final velocity minus our initial velocity divided by acceleration. Our final velocity is 0 minus our initial velocity of 20 meters per second divided by a negative 9.8 meters per second squared. And then when we calculate this out, we'll see that our time for the stone to reach its maximum height will be 2.04 seconds. In part B, we're asked to find the maximum height the stone reaches when thrown upward. So we're trying to solve for our change in height, which will be our delta y. And we can solve for height because we know our initial velocity times our time plus 1/2 our acceleration due to gravity times our time squared. So we have the information for all our variables besides our displacement in the y direction. Our initial velocity is 20 meters per second times our time of 2.04 seconds plus 1/2 times our acceleration due to gravity, which is negative 9.8 meters per second squared, times our time squared. When we multiply this out, we'll see that the maximum height that the stone reaches is 20.4 meters above the roof of the building. In part C, we're asked, find the time needed for the stone to return to the height from which it was thrown from, and find the velocity of the stone at that moment. So we found the time that requires for the stone to reach its maximum height, and since the projectile motion of our stone is symmetrical, we know that the time required for the stone to return from its maximum height to its original position is the same as the time it took for the stone to leave the original position to reach its maximum height. So on the way up and the way down, it took the same amount of time. So if we add 2.04 seconds plus 2.04 seconds, see that the total time for the stone to return to its original position is 4.08 seconds. And then we're asked to find the final velocity of the stone at that moment. So if we use our equation, of final velocity is equal to our initial velocity plus our acceleration times time. We know our time, our acceleration, our initial velocity, so we can solve for our final velocity. Our initial velocity is 20 meters per second plus a negative 9.8 meters per second squared times 4.8 seconds. And when we solve for our final velocity, we'll see that our final velocity for the stone at that moment in time is negative 19.98 meters per second. In part D, we're asked to determine the time needed for the stone to reach the ground. The equation we could use to determine the time required for the stone to reach the bottom of the base of the building, we could use the equation where delta y is equal to our initial velocity times time plus 1/2 our acceleration times time squared. We know our displacement of the stone is a negative 50 meters, since that's the height of our building, times our initial velocity times t, which we're trying to solve for, plus 1/2 times our acceleration due to gravity, which is negative 9.8 times t squared. If we simplify this equation and set it equal to 0, we'll see that we'll get 4.9 times t squared plus 20t plus 50 meters is equal to 0. We just set up our equation in the quadratic form. Now we can use the quadratic equation to solve for t. If we write our equation in quadratic form, we see that take our negative b, which is our 20, plus minus the square root of b squared, which is our 20 squared, minus 4 times a, which is negative 4.9, times c, which is our value of 50, taken to the square root, all over 2a, which is negative 4.9. If we take our positive square root, we'll see that t is equal to 5.83 seconds. We could take the negative square root, but if we did so, we would get a negative value for time. And since time can't be negative, this solution is impossible. Finally, in part E, we're asked to find what is the velocity and position of the stone at 5 seconds. First, we can try to solve for the final velocity of the stone after 5 seconds. So we know our initial velocity plus our acceleration and our time. We can solve for final velocity. Our initial velocity is 20 meters per second plus our acceleration due to gravity, and our time at 5 seconds. We'll see that our final velocity is equal to negative 29.0 meters per second. And then we're asked to find the position of the stone at 5 seconds. If we solve for our displacement in the y direction, we can use the equation where our initial velocity times time plus 1/2 our acceleration times t squared, we can solve for our displacement in the y direction. Our initial velocity is 20 meters per second times our time, which is 5, plus 1/2 our acceleration due to gravity times our time squared. We'll see that delta y is equal to negative 22.5 meters.